Good afternoon, all, and welcome to PIC Adda of this month, that is March 2022. This is Dr. Sangeeta Kale, Programs Committee member of PIC. With me on the panel, we have Dr. Vijay Kelkar as a panelist. Mr. Abhay Vaidya, Dr. Malik are also in the panel. PIC Adda is one program under Pune International Center, which is conducted once every month. PIC platform is very active in conducting programs, developing policy papers, conducting conferences, discussion sessions, and competitions on various topics of national and international interests. Social innovation, national security, energy and environment, science and technology, literature and culture, economics and politics are just a few to mention. I'm sure we all have studied, and few of us have even liked quantum mechanics during our high school studies. Though there may have been few of us who have even disliked the subject due to the long and complicated equations therein, we may all agree that the subject has a certain aura around itself. The connection of quantum mechanics to Einstein's theory and even to philosophy and spirituality have even been prominent reasons for our curiosity. In recent times, quantum technology has emerged with a new vigor due to the concepts of quantum confinement and quantum entanglement. In the topmost priority areas for research and development declared by the PSA Office of Indian Government, quantum technology tops the list due to its effect and contribution to national security, communication speeds, and advanced sensing devices. Budget of 2020 allotted rupees 8,000 crore to the National Mission on Quantum Technologies and Applications for a period of 5 years. Today, we have an excellent speaker who will throw light on these issues and the journey specificities on our PIC platform. We have the speaker for today, Dr. G. Raghavan, who is the Director of School of Quantum Technology at Defense Institute of Advanced Technology. He's a good friend of mine and a great colleague. Dr. Raghavan has trained himself at Baba Atomic Research Center. He's a PhD in physics from IISc Bangalore and 30 plus years of experience in nuclear research, condensed matter physics, and so on. He has been the head of theoretical studies at IGCAR, that is Indira Gandhi Center for Advanced Research in Kalpakam. He has set up one of the first laboratories for quantum information studies and semiconductor device structures and also on quantum optics. He has worked on deep submicron devices in Germany and is presently working in the area of quantum communications, sensing, and metrology. He is deeply interested in foundations of quantum mechanics and experienced research scientist and academic with a demonstrated history of working in the research industry. He's a skilled person in quantum optics, quantum information theory, nanomaterials and computational physics, material characterizations, and so on. We welcome you, Dr. Raghavan, to this platform and request you to deliver your talk. Over to you, Dr. Raghavan.
Thank you very much, Professor Kale, for a very, very kind introduction. I'm not sure I'm going to live up to this billing because I've had some problems at Chennai with the unannounced power cuts, and I have been able to put up something together. So let me at the outset apologize to everyone for starting this talk late, but I guess it's I take refuge under force majeure over which I didn't have much control. So just give me a minute. Let me share my screens and I will start with my lecture. Give me a couple of minutes, please.
Yeah, sure.
The full screen. And go to your movie. Uh, Good afternoon, everybody. I hope you're able to see my screen with an apple on it.
Yes, yes, yes.
Okay, let me start. So first, I should thank my son Vakul for adding some nice graphics. I didn't give him much time to do this because I had just a half a day to do this. Let me start so that it doesn't become the usual just boring PowerPoint presentation. We have this apple that is the apple. There is a historical significance in the hagiography of physics. We all know how Sir Isaac Newton was inspired by this singular fruit, and we hear stories of how it fell upon his head, and lo and behold, that we had the theory of gravity that Newton came up with. But hagiography is notwithstanding, there is one notion I would like to start with, the notion of what exactly an apple is. What constitutes the very real presence of an apple? An apple, you should see, is just part of the phenomenal world we experience. A phenomenon is presumably there's an object underneath that is then having a laundry list of properties or attributes. The apple has certain color, certain texture, and so on. And we believe that these properties are out there resiliently attached with the object, and they exist, such as the apple's beauty has a reddish hue and texture to it. And these are properties of the apple that exist independent of whether we observe this apple or not. But what are the manifest consequences of such a position? For instance, we say an apple is either red or green or some odd color, but it's vividly so that this attribute of color has a definite value. We can ascribe a certain number to it. And this number to this property is a property, one of the properties that define the apple itself. We experience in the world of phenomena a whole set of attributes. And we assume that these attributes are there, that belong to the object, and we merely, when we look at them, report that they have these and that property. In other words, our observation merely certifies the existence of these attributes. But this is one position where we say that these properties are out there. An apple is out there with all these properties, or a moon is out there with all these properties, independent of whether we observe them or not. And the observational process merely certifies the existence of these properties with a certain value. But is this really right? This fundamental question is raised by quantum mechanics. We seem to say that objects or phenomena as we experience is a laundry list of attributes, that these attributes do not have a prior value. A priori, they don't exist in any different state, but actually they exist in a huge set of potentialities, potential values for these attributes. And one of these, with a complete randomness, utter, complete, total, whimsical randomness, manifests itself just at the time of observation. It's concomitant with the observational process itself. In other words, observations manifest the property or the phenomenon itself. Now, if you hold on to the view, look here, all these objects that we have in this classical world do not have this weird property. They are resiliently out there, independent of measurements or not. But why is the quantum state so? Well, this can be demonstrated through experiments. That this is indeed the case when we look at very tiny objects at an atomistic scale. But then this throws us a big challenge. When we look at the macroscopic world, after all, it's an agglomeration of atoms and microscopic entities. And if the laws of quantum mechanics are universal, we need to explain why the classical world, the world of large things, looks so eminently classical and does not share this property of being attributeless until an observation is made, and that the very act of observation randomly reduces to one of these properties. Now, this is what is one of the strange weirdness of quantum mechanics. Let's go on and look at the apple a little further. And you see, what are the ideas that existed much earlier to modern notions of quantum mechanics? The path of discovery of our entire world could be a rational exercise. And through this rational exercise, we can have a clear logical understanding of the interrelationship between phenomena and a deterministic explanation of the world around us. And we can even be able to control the flow of things. This is a great enterprise taken up by Homo erectus, our species, and we have done brilliantly so till now. So let us now trace back to the history of how ideas evolved, and then so that we may locate the present state of things with a little understanding about how the historical development actually took place. Now, we know that matter is composed of material particles. Democritus postulated in ancient Greece the atomistic theory that ultimately everything is composed of particles, in itty-bitty particles put together to give gross matter. And this was a revolutionary great idea, that there are fundamental units that go to constitute macroscopic objects, because it is a sense of great wonderment to the ancients. On the one hand, we have the robust resilience of the phenomenal world. At the same time, we know things grow, are born, grow, they decay and die. And therefore, there's a disassemblage of these objects. And this is something they try to reconcile, the extreme robustness and resilience of the physical world with the constant change that we are able to see. And the atomic theory over the ages gave us a clear understanding how exactly this happens. And therefore, now came the question that, okay, the material world, as it slowly evolved, is made of these fundamental units called atoms. And then much later on, I'm not going through a linear narrative history, we know that the periodic table came about, and then we understand now that matter is made of atoms. In fact, Feynman said that if you have to send a tablet into outer space, the one message that we would like to communicate to the aliens is that we know that matter is composed of atoms. Yes, matter is composed of atoms. Matter at a larger scale is experienced by us as phenomena. But how exactly does this information transfer occur? There ought to be a medium or a means through which we can receive information. The ancients wondered, for instance, at how visual perception actually occurs, how we are able to perceive an apple as such, this color, texture, and so on. That something must carry this information to the waxen plate of our mind, as Hume postulated, and somehow record these impressions. And somehow this data becomes capta, the formed a concept and a classification of objects such as apple, horses, and whatnot. So how does this phenomenon take place? So there must be some intermediate agent that communicates to us the properties of external objects, and that makes us form impressions of them. So one of the ancients postulated, like Aristotle thought that something emanated from your eye and then bounced back from the object, carried this information by transforming itself and going back to you into your eye. This is called the extroversion theory, as something that emanates from your eyes and then that impinges on different objects, and they're getting reflected back somehow mysteriously, carrying with them this information and then transferring it onto your internal vaccine plate of your mind. Now, this was an extraordinary thing to say. First of all, the central idea was that they recognized that there has to be a medium that actually communicates with the object between you, your eye, and the object, and carries back this information. This is an extraordinary step forward. Now, if this is really true, then we will come to the extraordinary situation that perhaps Aristotle had observed the cat's eyes in the dark of big cats, and they were shiny, and he concluded that his extroversion theory was actually right. But then this would have all the perceiving individuals as being sources of bright light, shining forth through their eyes, and this is not what we observe. So the extroversion theory at a gross level is clearly wrong in our understanding of how perception comes about. But at least for an early theory, this was an advancement in the sense that there is a signal that is transacted between us and the objects that carried forward this information. So this was, one could say, the earliest understanding of what the role that light played, and one can extrapolate it to sound and other sources of our sense organs, how the information is transacted between the external object, whatever it might be, but its attributes that constitute phenomena are brought back to us, and we form a very coherent picture of the phenomenal world. So there we have one of the arguably the greatest thinkers, the greatest physicist of all time, Sir Isaac Newton, and his great work, the Principia, that started with the question of why objects fall under the influence of the gravitational force of the Earth. And then this great leap that identified the forces that held together the planets in the solar system as being the same one that makes apples and objects to fall on the Earth. So the Principia is historically one of the most important documents. Of course, there were other great thinkers like Christian Huygens, who also in France worked on issues of celestial mechanics and mechanics, gravitation, and so forth. And slowly, we had a clear idea how to reconcile astronomical data. Of course, ancient civilizations like the Indians, and before perhaps the Babylonians, the Chinese, and the Greeks during the Hellenistic period already had some idea. Some would even say that the heliocentric theory was already well known in some of these civilizations. But it came to definitely Europe after the Dark Ages through the very systematic work of Sir Isaac Newton, Huygens, and others. And other than his contribution to the theory of gravitation, the idea that the force is something that is involved in change of motion, Sir Isaac also worked on the issues of what exactly was light. And he postulated an atomistic theory of light, and he called them corpuscles. And then these corpuscles were something that were being communicated. But he did not postulate an exclamation theory, but rather he said that these sources of light are there, and he systematically and experimentally investigated the phenomenon of how light interacts with material objects. And he says light is constituted of these itty-bitty particles of radiation that he called the corpuscles, and the corpuscles are moving forth. And then he had to explain how color was formed, how light bent at the interface between a rarer and a denser medium, and so forth. But in investigating this, Sir Isaac, his genius notwithstanding, came up with a wrong theory. In the sense, his theory was not ratified by experiment. Sir Isaac postulated that these corpuscles, when they impinge on material objects, actually travel faster in media than they do in vacuum, which was clearly proved wrong by early experiments that try to measure the speed at which light was moving. This itself is a very wonderful question. Does light move with a very definite speed? Light is very fast, obviously, but how fast? Does it have a finite speed? And these were investigated, and fairly good experiments were done to come very close to the current values for the speed of light. But basically, the corpuscular theory was wrong, and it was at variance with the experimental facts. But an alternate theory was proposed by Christian Huygens in France, and where he postulated light was like a wave. It was not a localized set of particles, but rather something that extended as a wave. And the waviness, of course, he did not at the time have an explanation as to what they were waves of. And basically, perhaps he borrowed an analogy of waves in water. And one of the properties of these waves is that we can have two disturbances, and these waves tend to overlap and interfere with each other. So Christian Huygens provided a theory that was at variance with Newton's own corpuscular theory, where, as we said, that light seemed to travel faster in medium, which is clearly wrong. And Christian Huygens' own ideas were then further experimentally investigated by a scientist called Young in a very simple and neat experiment. If, as we know that in water waves, we create 2 points of disturbances, 2 wavefronts start moving, and they were restricted to 2 apertures, 2 slits as it were. And these 2 waves again generate further waves beyond the slit, and they overlap with each other. In some places, they overlap in such a fashion that the higher points of the wave also overlap the higher points of the other wave. Then they reinforce or strengthen each other. And sometimes it happens that the higher points of one wave actually overlap with the lower points of the other wave, thereby destroying it. Therefore, we would have dark and bright areas that are there described on the screen further down. We call this phenomenon interference pattern. And this interference pattern is very typical for waves. And Young did an experiment and actually showed that making 2 small slits, that one can have a source of light, and that light passing through these slits actually produce an interference band, which was something typical of waves. And therefore, it was sealed for a long time, a settled issue that light was an extended wave-like objects. We still didn't know, and they had to wait until the arrival of the theory of electricity and magnetism, and again, under the very brilliant scientists who investigated and unified these ideas, the experiments from Faraday, Hertz, and many others, and identified that later on, it turned out that light was a part of what we call an electromagnetic wave. And this is, again, one of the major findings that progress was built upon later. So there we have this great scientist Christian Huygens, and their rivalry was known and celebrated all over Europe. Two great minds that came together to give us an idea about celestial mechanics uh, and about the nature of light itself. Here is again a visual of how this sort of interference pattern actually forms. So here we have, supposing not a continuous stream of light, modern experiments show that we can attenuate light such that we have again a granular nature of light. We call it a quantization of light. We call these small packets of energy, radiative energy, as a photon. And then we seem to again, through the ideas of Einstein, who investigated some phenomenon called photoelectric effect, wherein when you shine light, it ejects electrons out of metallic surfaces. And that, I will not go into the details of these ideas, but it gave rise again to a particulate nature of radiation. And then now we are at a level where we can actually send one light particle after another. In other words, we can have a photon gun. A photon is that smallest packet of energy, and send it through our double slit experiment. And these experiments are something that we can perform in the lab, and we have something extraordinary happening. For one thing, when we do this experiment, one photon at a time, we have to ask the question, through which hole does the photon go? Now, if you try to find out, then we will have blobs of light here and here. We don't see any interference fringe. On the other hand, if you don't try to find out through which hole that the photon has gone through, on the screen farther away, you have just one dot that is recorded for that photon. Then we send in another. It records another dot on the screen, yet another, and another dot. But we wait patiently. When large enough number of these photons have been fired one at a time, then we slowly see the fringe pattern emerging. That's pretty strange, because we said that the fringe pattern is a property of a wave. But here we are firing a particle-like object, and when we don't try to find out through which hole it went, it behaves like a wave, at least a cumulative wave effect does, even though the individual record is that of a point recorded on the screen. But eventually we have the interference fringe building up. On the other hand, when we know through which hole it goes, our knowledge, our very knowledge of this inhibits the appearance of this interference fringe. This extraordinarily strange and schizophrenic property that light could behave like a wave in certain experiments, depending on what we choose to learn about it, and behaves like a particle in other cases. So the question is not the initial dichotomic aspect. It's either a wave or a particle. You say either it's both or it's neither. Whatever, the experimental conditions determine which properties manifest. Again, this is an extraordinary property that is quite natural to quantum systems. So this type of dual existence. But what happened historically, sometimes around 1905, this humble patent clerk, once again, Albert Einstein, we celebrate this year as the wonder year because he comes with 4 extraordinary papers. One of them proof through his investigation of what is called Brownian motion, of how pollen particles move randomly, seem to move randomly under the microscope. He establishes very firmly that matter is atomistic. There's another paper he writes for which he got the Nobel Prize, because people were pretty unsure about the special theory of relativity thing. At that time, it was still very much of a debated thing. So the Nobel Committee awards him a Nobel Prize for the photoelectric effect, which brings out the particulate nature of light. The modern experiments show that both of these properties exist. It's around this time, the early years of quantum theory, that Francis Broglie, a part-time physicist, comes with the brilliant idea that matter could also exhibit this dual property of being a wave sometimes and behaving like a particle. And we see indeed that we can do double slit like experiments with atoms and show that the interference fringe again builds point by point and obeying all the properties that we see light to behave so. We can even investigate with much larger molecules like the fullerene, which is a football-like molecule, with a large number of 60 atoms of carbon come together to form this molecule. One can again produce interference fringes again. But a big object like a carbon-60 ought to go through one slit or the other. But we try to find out again, the interference fringe disappears. We don't try to find out, there's no way of finding out. Then we see that the interference fringe is restored. So all this is a matter of experimentally verifiable facts that we can perform in an undergraduate laboratory. At least some of them, those experiments with electrons and photons can be done. Now we come across a little more complicated experiment here, the type we perform in our lab. We have this slit, and we have behind the slit a crystal, what we call a nonlinear crystal barium borate. And then this crystal has an extraordinary property that when you fire this pump it with light, and for each photon, let us say blue in color is dictated by the frequency. For those technically minded, you say that in terms of wavelength, we fire a 405 nanometer photons, then it splits into two beams. We can arrange it that these two beams have particles or photons with 810 nanometers. So two red photons are produced occasionally for every blue photon that impinges on it. And these two photons, red photons, have the extraordinary property, quantum mechanical property of being entangled. Entangled in the sense that the property of one somehow is very deeply entangled with the property of the other. Now, what quantum mechanics says, as we've already seen, there's no existing reality out there, but reality is something that happens randomly. We saw in the case of the apple, the color is something, the many potential colors that upon an observation we get. We have something called a polarization of the plane in which these electromagnetic oscillations happen. The electromagnetic particle, the photon, inherits this property, and we see that the polarization can be oscillating in a plane this way, or this way, this way, or this way. When we ask each of these photons which way it is oscillating, we do not know until we make an observation. But when we make an entangled pair, we can be sure that both of them have these two possibilities of being up, up, and side, side, and up, up, and side, side. But however, we can arrange it that upon an observation, if this turns out to be up, down, this should also turn out to be up, down. But this occurs very randomly. Remember that upon an observation, it could have turned out to be this or this randomly due to the utter whimsy of nature. But however, we see that these two particles can move as far away as possible from each other. And if I wish to find out what is the status of my photon, I have to measure this, observe the polarization of this particle. And if I find it to be up, up, the other photon, wherever it is, it's in another continent, maybe in the Andromeda galaxy, it doesn't matter, instantaneously goes into the corresponding up state. On the other hand, if this it turns out it is in a back and forth motion, or the motion side to side, and upon an observation, randomly we see that it's side to side, the other photon, its twin, wherever it is, again will turn out to be side to side. Now, is this extraordinary entangled madness really true, or is it a prediction of the theory? In the last 20 years, beautiful experiments have been done to show that it's very real, and this sort of an entanglement is there for particles of light, for material particles, and so on. And what more, we can make use of them in building computers of a completely new type. We can do provably secure communication, and we can do extraordinary feats of sensing that are not classically possible. And much of modern day quantum technology depends on this extraordinary resource of an object being in a superposition, what we call a coherent superposition of many possible or potential states, and an observation resulting in a particular one randomly, and this property of entanglement. These are seen as resources, and we have a complete, well-organized resource theory based on which we can know how to manipulate this object and build technologies around them. So let us get on with it, where we pump in 2 photons. And once again, this also splits into 2 parts. And here we have a lens, and then the lens converges these 2 beams into a photon counting detector. It counts 1 particle at a time. Now, since these 2 beams are focused into a particular point, the path to which these 2 photons arrived is effaced or erased. So we do not have any information about which path the information came from. The photon could have come through this path to here or through this path to here, but since both of them are focused at this point here, if the detector clicks, we have effaced all information about the path. Now you take the twins of each one of these photons, and then we make them impinge on mirrors here, and then we collect them here. And we can show that by moving the mirror. If we retain the path information, we can again have the path information. And if you have a double slit here, then we will have an interference pattern. On the other hand, if we erase the path information, we'll have the interference pattern. If we don't erase this path information, then we know through which path these photons came, and there is no more any interference fringe. It's like finding out for this photon which hole it went through. Even though we are doing nothing here, but we are doing it remotely to a photon perhaps hundreds of kilometers away, we can make this information of there being an interference fringe or not to be erased at there. This again is an extraordinary trick that can be performed and experimentally demonstrated. So this is a 50-50 chance that these are called partially silver mirrors, called beam splitters, that we can detect to send them to 2 other detectors and bring out this property of whether both these go here and path information is effaced or not. I won't go into the details of this particular experiment, but such experiments go under the name of Welcher Weg, or which way did the photon go. Now, so long as there is no possibility of even finding out which way the photon went, it will behave like a wave, and if we can at will erase this which way information and produce a particle or wave-like character. Yeah, so let me so these are some of the very strange aspects of our quantum theory. Like I said, to recall, we do not know that there is a reality out there, but reality is manifest upon observation. And what particular physical attribute that comes out seems to be completely random, a matter of chance. This gave rise to the very famous and oft-quoted saying by Einstein that God does not play dice. And that Einstein could not somehow reconcile to the fact that the physical theory, an extremely successful theory, the quantum theory, which works at subatomic levels to the cosmological scale, somehow has nothing in it that will tell us whence this randomness. That something was inherently, unpredictably random, because all randomness that we encounter in a classical world are born out of ignorance. When I toss a coin, I do not know whether it will turn out to be heads up or tails up, only because of an absence of information. We presume that there's a deterministic process, and if I had all this information, I'd be able to precisely predict it'll end up with heads up or tails up. But quantum theory says that nature is inherently whimsical. She decides just at that moment to go whichever way she wants. So Einstein had serious objections that nature could behave this way, and our theory could say go thus far and no further. And therefore, he believed that the quantum theory, for which he also greatly contributed, was an incomplete theory, and we have to look for something beyond the quantum theory. So then gave rise to a lot of speculations of how to complete the quantum theory. Now, the question arose, therefore, whether the only way of seeing is that there are two processes where the quantum system keeps on evolving, and there is an upper process when we try to measure that it reduces or collapses to one state. Now, therefore, the ideas by Niels Bohr and others, they said that the world has to be divided into a quantum world and a world of classical objects, where the measuring apparatus were huge and not described by quantum theory. And that is not a very happy situation because nobody knows where this border lies between a classical object and a quantum world. We do not even understand today whence the very resilient classicality of our world, even though the underlying laws should be those of quantum mechanics. But this gave rise to other bizarre theories. For us, that of course we have this quantum entanglement, that particles arbitrarily far away could be correlated when we make measurements. To one way that Hugh Everett, a very brilliant physicist, said that among the huge set of potentialities, every potentiality actually manifests in a different world. That the world, as it were, the universe, as it were, continuously branches out into many parallel universes where we are in a particular branch or where we have a particular set of values for what we measure. But in another branch, the other possibilities arise in yet other branches and so on. This has, of course, been the gist of many Hollywood movies till today with Spider-Man, multiverse theories and so on. But it's a little far from the actual theory, but it's an extraordinary theory. There have been many other explanations to try and understand nature's whimsy, this massive parallelism and so on and so forth. But none of it really at a foundational level is hugely satisfied. Now, so these are some aspects that we have to reconcile with. Not only does God in fact actually play dice, he seems to be an inveterate gambler, that nature seems to be inherently whimsical and random. So what makes nature behave this way? Could we understand her better? What lies, the secret that lies behind this extraordinary partial visage phase of nature that we see? This is something that intrigues all of us as physicists, but as technologists and more practical-minded people say, how can this be exploited to build more powerful computers that can do what classical computers cannot do? How to make provably secure communication. For instance, if quantum computers of a significant size are available, much larger than the ones that are being currently made, we can break most of the current known encryption techniques very trivially. Not all, but many of the popular ones can be easily broken. And that poses a serious question of information security, with which, of course, governments are concerned, military intelligence, and so on. And therefore, the twin possibility of making computers that are massively parallel using quantum resources could give us an access to things that are not computable classically. And also, we can also secure our information in a provably secure fashion if quantum resources such as entanglement and the fact that quantum states cannot be copied or they get disturbed upon measurements can be used. And they are commercial solutions where this quantum key distribution or quantum cryptography, to put it more broadly, actually is available to us. And we too are building such solutions. A third and final aspect where, again, this plays a very important role. I've talked at length about the interferometers. Atoms, as I said, material particles also have wave-like properties, and therefore we can build atomic interferometers. These are millions of times more sensitive than interferometers will be built with light, and that gives us access to measuring in a very fine fashion minor changes in gravity, and therefore we can use atomic interferometers for gravimetry, rotation, positioning, where GPS is not involved. Again, this is something military people are greatly interested in, locating in a GPS-free fashion our submerged and submersible assets elsewhere. So this gives rise to a whole host of technologies which are actually practically realizable. So I will stop here and just end with a quote from one of my favorite polymath thinkers, Al-Hassan bin Al-Haytham, arguably the father of modern optics, who wrote more than 10 centuries back in the Abbasid Empire, a book called Kitab al-Manazir, where he investigated optics and wrote multiple volumes on optics. Al-Hassan says, for a man who investigates the writings of scientists, learning the truth is his goal, is to make himself an enemy of all that he reads, and applying his mind to the core and margins of its content, attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency. I think it is an extraordinary statement coming from a thinker more than 10 centuries ago that we ought to take any authority at the face value. We have to, in the strangeness of things, keep on investigating, doubting everything that has been said and done, and even doubt whether we are performing this job correctly or so. In fact, in defense of why we should be men of science, and there is an age where, again, people who are the religious, extreme religious bent of mind said that it is anti-God to look at a rational explanation of things. Al-Hassan said, if in wondering about the creation, I'm just freely quoting about the creation of God, about the effulgence and the brilliance of his creation, it is then what I'm doing is seek the truth. And this is the ultimate reason why we should actually look at things and try and find explanations for things, even those which are most intriguing and counterintuitive to us. So with these ideas, these thoughts, I stop now. I'm sorry for a rather incomplete presentation. And Professor Kale told me that we have a mixed audience. No equations, all equations are forbidden, nothing technical. But this is the sort of excitement that is at the basis of all that we do, the fun of it, and also the possibilities that we are a part of an evolving technological revolution, what we call the second quantum revolution. Thank you all for your patience. And once again, sorry for the delay in my presentation.
Thank you, Professor Raghavan, for a very, very interesting talk. And I would like to say that you have tackled a very complicated subject in a very simple manner, starting right from a simple apple, the way in which you are able to see the apple, the color, thereby going towards the concept of light and the vision. And from there on to optics and the concept of constructive and destructive interference, and thereby going to the double slit experiment. And then the concept of seeing a photon is also kind of destroying the kind of information that it is trying to give us. And then the concept of quantums and the quantum entanglement. It's a wonderful journey through which you took us through. It was really a difficult task. I'm sure all of us would agree to take us through this journey. It's not easy. So thank you for giving this wonderful insight to the concept of quantum mechanics. I myself have one question which is related to the national security. and also the preparedness of our country in order to handle this complicated topic and thereby the technology. So the question is that how do you envisage India in terms of this quantum technology, and how prepared are we vis-a-vis the situation of the other country, and the way in which they are prepared uh, with respect to the technology such as quantum technology, typically related to the defense, security, as well as the communications part, because these are the two areas in which I think quantum technology is going to have major impact. So can you throw some light on these two issues in the Indian context?
Thank you very much, Professor Kale, for this question. Over a period of time, I've had occasion to interact with people at various higher levels of planning, be the office of the PSA, the then PSA, Dr. Chidambaram, the current PSA, where I given a talk at one of the institutions, or the defense establishment, others. There is a serious and growing interest, especially impelled by the government, to get our act together. But the fact is that we are at least 2 decades behind in this game. We have started out too late. And quantum technology, quantum is just one part. Quantum machines such as these are extreme devices in that they work at a single photon, single atom, single molecular level, and where we need to exercise extreme control to ensure that the large external world does not somehow impinge on the very fragile quantum states and destroy them. We call this process decoherence. And therefore, these experiments are quite often done on quantum objects in these extraordinary states at very low temperatures, in the order of millikelvin refrigerations and so on. Is the fact that these technologies also involve chip design and making, which we have very little legacy. We don't have a single super fab in this country, where a country like China has, I think, 12, 14, 15 super fabs that can manufacture devices, line definitions of 5 nanometers, which is much less than the size of most viruses. And when you go below this level, the real quantum effects start to kick in. Now, unfortunately, we have not even gone into deep submicron. We don't have a huge fab. The present government is trying to address this question because it requires huge investments and so on. But the fact is that this is a technology that we lack. It's not just about the physics of it, but actually the technological realizations in terms of fabricating very sophisticated structures. We do not have refrigerators that go to millikelvin level. We have to buy them. We do not produce lasers in this country that are very special and required for many of these technologies. So there is a huge gap that needs to be filled. And this is the most challenging part of not just doing a lab level demonstration or a proof of the principle, but actually working technology. These are huge challenges, and the current methods of just distributing funds over a variety of institutions, well, they would augment a critical infrastructure in that we create more and more laboratories and then train more young people. All this is required. But in realizing technology like quantum computers, this is not going to be very easy. Where quantum communication is concerned, the outlook is a little better. There are many people who are working on quantum communications and cryptography. Quantum sensing, there are groups that work on cold atoms and cold atom interferometry. Again, to apply them for very specific technologies is requires a miniaturization and to make these solutions mobile. And this is an area, again, of technology that requires a great deal of attention.
Okay, we can say that for national security, we have a long way to go. Do you see any major institutions or companies or industries who would be, coming up in the recent times with a good impetus given by the government of India? Do you feel that there would be some major institutions or industries who would be emerging in the recent time? I hope
Yeah,
the question is.
again, a good question, because if you see in the West, barring China, where the entire program is fully funded by the government, but they had a plan for over 3-4 decades where they sent their scientists, military people, disguised as students and whatnot, all over the West and US, got them trained there, and then brought them back and set up laboratories of the type they were working on, and even got people, paid professors and others in the West, to set up such labs in China. And as a result, they have overtaken even the West, in my opinion, in many of these technologies. So they had a long-term strategy. But with regard to the Western countries, other than governmental institutions, bulk of their funding comes from the private sector, like Google, IBM, Amazon, a host of other people, Microsoft, and other startups, big and small, are all getting their act together and becoming a part of a huge ecosystem in which huge amounts of funding is taking place. Unfortunately, the Indian industry has never been there at the helm of trying to fund R&D. We seem to have large industries that are more interested in buying technology and marketing them for a very large market. This is unfortunately the case, that we don't have industrial R&D of a scale where we require contributions from them. So this is a matter that I was invited by NASCOM to talk about the potential markets and so on. Among others, I had also given my inputs for what it mattered. Again, there's a huge gap, because funding by government agency alone is not the way to go. But again, I do not know what the solutions are.
Yeah, I agree. There's one question, probably the last question from Dr. Ashok Kaushal. He's asking, from your understanding in quantum mechanics, do you wish to dwell on spirituality?
See, this is sort of a double-edged sword, where genuine spirituality, I believe, is my personal belief. That's why I gave this quote from Al-Hasan, that when we wonder about nature, about the foundations, about how things work and so on, that is a sort of a spiritual quest. And without giving it any religious color. Religions, of course, are different, but spirituality per se, yes, it is a spiritual quest in a very deep sense of the word. And this is something that also greatly influenced many great scientists in their ways of thinking. In fact, you could often see that many of these scientists were greatly influenced by Eastern philosophies, our own logical systems, and even to current day, there are scientists like Anton Zeilinger and others. There is an interview where Zeilinger, one of the major contributors to this field of quantum information, is talking with the Dalai Lama, because he has found that Western philosophical ideas in logical systems do not really provide us a deep enough insight. We have to seek all possible inspiration at how exactly we make sense of this extraordinary state of things. If an understanding, in trying to understand this, not, of course, belittle this thing by doing sort of a pop science, or sort of becoming a religious zealot who says that everything is known to the ancients. Short of that, I think, I personally believe, and for me, personally, a deeply spiritual quest more than anything else. And I'm sure people who investigate the foundations of phenomena, people with far greater equipment and intellect than mine, are also deeply influenced by such ideas rather than merely by technological development. Yes, to answer your question, yes, spirituality is something, an integral part but one has to then define what constitutes that philosophy for or the philosophical or sort of spiritual approach for an individual, and that could vary from individual to individual. I will be more than happy, since it's an Adda. You can be absolutely free to ask me questions. I cannot claim to be an authority in anything, but I can definitely, I have very strong views of my own, and I'm available to, ask many questions as you want. If you have the time, so do I.
Yeah, sure. Actually, I'm sure that with this recording and people would want to listen to it once again and, try to come back to you. So they will definitely come back to you with many other questions. I'm quite sure, because it's a very vast topic, and some of us in the audience would take some time to, grasp it and digest it and come back with the questions. But I would. There's somebody who has raised the hand. I would request the person to express a view. Is it Mr. Pathak? Mr. Pathak? I'm not able to hear. Anyways, I think those who have raised the hand and those who are not able we are not able to hear anybody, they can put the questions in the chat box, or you can directly write to Professor Raghavan. We'll share the coordinates of Professor Raghavan with everybody on this conversation. So let me formally thank you, Professor Raghavan, for this extremely good talk. And it was a complex topic, I'm sure people would agree, but you made it very lucid, very simple, so that all of us could really understand it well. So on behalf of entire Pune International Center, I thank you on my personal behalf as well as on the behalf of the panelists who are there today to have you on this session. Let me thank you, Professor, for a very, very good talk. Thanks a lot. And to all the participants here, before we end this conversation, let me just take you to the next event of PIC, which is a roundtable event on Industry 4.0, a roadmap for India's global leadership. This is being arranged on 23rd of March, that is coming Wednesday at 5 o'clock, so 5 to 6:30 p.m. Do join in for this particular program, which is chaired by Dr. Mashalkar. The paper is presented by Dr. Arvind Chinchure, and there are panelists, Dr. Ijaz Dhani, Ms. Rujuta Jagtap, Mr. Amit Paranspe, and Mr. Madhukar Kotwal. So this event is to be scheduled on 23rd of March at 5 o'clock. So do consider attending this event. And thanking you once again, Dr. Raghavan, for a very interesting talk.
Yeah, thank you again, Professor Kali, for this wonderful opportunity. Maybe we'll get across and have person-to-person Adda sometimes. That will be better than this electronic medium. Is rather restricted.
Yes.
And I also thank the members of the Pune International Center for giving me this wonderful opportunity. We can continue this dialogue further. Thank you very much.
Thank you. Thanks a lot. And goodbye. Bye-bye.
Thank you.